This is Project 4 by Team 2. My name is Brian Crandall. First, we'll talk about electron configuration, which is the arrangement of electrons in the orbital of an atom. It describes how electrons are distributed in the various energy levels called shells and sublevels called orbitals. We'll focus on orbitals, which are within each energy level. Electrons are further arranged in sublevels. First is the S, which holds 2 electrons in their orbital. P can hold 6 in their orbital, D 10, and F 14. Looking at this chart, it's the best way to explain it. It just follows this pattern as seen right here and to the left. Usually you'll be in the 3 to 4s range, sometimes even smaller than that, like we'll see in our examples. So aluminum contains 13 electrons, and using that pattern as before, we go to the 1s, the 2s, the 2p, the 3s, and then we stop at 3p, and we only put 1 in that orbital because there's 13 electrons. Same thing with magnesium. It has 12 electrons though, so we stop at the 3s, we don't go to the 3p. Boron contains 5, we stop at 2p, and nitrogen contains 7, so we stop at 2p as well, and go 3 instead of 1 because this has 2 more electrons. A band gap is the energy difference between the valence bond and the conduction band in a material. Small band gaps, typically in the range of 0.1 eV to 3 eV, typically semiconductors, which we'll focus on. Large band gaps higher than 3 eVs, typically insulators. Semiconductors have a small band gap allowing for controlled electron conductivity, which can be manipulated by external factors like temperature. Looking at examples, we have to use the solid state of nitrogen since in its molecular form N2 does not have a band gap. So solid nitrogen at a low temperature usually has a typical value of 1.6 eV, and boron is in its crystalline solid form, is a semiconductor, and has a band gap that varies depending on its allotrope and structure. This commonly referred form is a alpha boron. This have a typical range of 1.5 eV. Electronics is the branch of science and technology that deals with the design, development, and applications of devices, circuits, and systems that use electrical energy to control and manipulate the flow of charge. So a great way to look at this is the application of ICs. So nitrogen can be used for IC packaging of integrated circuits and the other delicate electronic components to prevent moisture. Then boron is used in some applications to modify the gate, oxidizes, and MOSFET devices, which are important for controlling the flow of electrons. So as you can see, semiconductors are pretty important for electrical circuits. And looking at LEDs is a type of semiconductor device that emits light. Think about the normal lights you maybe put in your room as a good example to think of this. It's a wide range of colors due to their properties. So looking at nitrogen, plays a significant role of indium nitrate and gallium nitrate. These usually are a mixture of blue to white colors, and nitrogen is a key factor in the component of synthesis of GaN. So this is how nitrogen is used in LEDs.
Doping of semiconductors. Semiconductors by themselves only conduct a small amount of electricity. However, their conductivity can be changed if we introduce impurities by doping them with other atoms. The one type of doping is called N-type doping. N-type doping involves introducing excess electrons or negative charge carriers by adding donor impurities. This is done by introducing an impurity that has more valence electrons than the semiconductor. The other type of doping is called P-type doping. P-type doping involves introducing holes or positive charge carriers in the structure by adding acceptor impurities. This is done by introducing an impurity that has less valence electrons than the semiconductor. Our two semiconductors are nitrogen and boron. For p-type doping with nitrogen and boron, we can choose aluminum because it has less valence electrons than nitrogen, which will create holes within the nitrogen and boron structure. For n-type doping with nitrogen and boron, we can choose phosphorus because it has more valence electrons than these semiconductors and will allow for excess electrons to move around and increase conductivity. You can see in these diagrams of the atomic structure of nitrogen and its dopants. On the left, you see n-type doping of nitrogen with phosphorus as its impurity, and you can see the free electron within its structure. On the right, you can see p-type doping of nitrogen with an impurity of aluminum, and you can see the hole it creates within its structure.
Applications of boron nitride. Boron nitride is gaining interest in optoelectronics such as UV detectors, LEDs, and transparent membranes. This is due to its unique properties of having one of the widest band gaps among 2D materials. This allows it to absorb and emit light in the deep ultraviolet region. The defects within it can be engineered to produce single photons at room temperature, which opens possibilities for quantum photonic applications. Its high thermal conductivity is also good for dissipating heat in optoelectronic devices.
Everybody, my name is Emin Skiljan. Today we're going to be going over question 4, project 4. So, what are the mobilities, concentrations, and electrical conductivities of free electrons and free holes, respectively, for your intrinsic semiconductors? So, before going over which semiconductor we have, we're first going to go over what each term means. So, mobilities in semiconductors describe how quickly change carriers, electrons, and holes can move through a material when subjected to an electric field. The concentrations of free electrons and free holes in a semiconductor depend on whether the material is intrinsic, pure, or doped extrinsic. The electrical conductivity of a semiconductor is the sum of contributions from free electrons and free holes. So our semiconductor is HBN, hexagonal boron nitride. So we chose this form of BN due to it being one of the most common forms of boron nitride and the vast available information on it. So the two main equations we're going to be using today are the carrier concentration equation and the electrical conductivity equation. So for carrier concentration, before calculating it, first we'll analyze the equation and analyze the E component. We can see that E sub G is going to dominate the question, therefore we can focus solely on the E and its exponents. So after we plug everything in, we can see that E is going to be raised to the power of negative 114. So this number is effectively 0 due to how small it is, so it can be concluded that the intrinsic carrier concentration is 0. If it was doped, all the results, including this one, would be varied, and we'll see that later on in the project as some of the results we will be doing in consideration to doped numbers. So mobilities. Due to the conduction being so low in naturally found hexagonal boron nitride, mobilities are negligible. However, in engineered or doped HBN, the reports of mobility have been as such, and I got this information off of studies done online, as this isn't something you can really just calculate at home. So for electrical conductivity, we have the two different results. So for natural HBN, it's going to be right about 0, but for the sake of the experiment, we'll also consider a doped HBN. And so the result we get there is 3.2 times 10 to the negative 5th, S divided by centimeters. And so the 10 to the negative 12th was just a hypothetical electron concentration, and that was just to be able to solve the question. Overall, HBN is usually going to have a low electrical conductivity, no matter what the electron concentration is going to be in its place. So we have a few different uses of HBN, and we're going to be going over it in electronics and LEDs. So HBN is an excellent insulator with multiple uses in electronics. It's a substrate for 2D materials. HBN provides an atomically smooth, defect-free surface for 2D materials like graphene and transitional metal dicollagenides, TMDs. Thermal management with high thermal conductivity and electrical insulation. HBN is used in electronic packaging as a thermal interface material to dissipate heat in high-powered devices. And at the bottom right, we can see quantum light emitters and how it's used in the makeup of HBN. And so uses of HBN in LEDs, they exhibit chemical and thermal stability, making it a great candidate for LEDs. For deep ultraviolet LEDs, monolayer HBN exhibits a direct wide band gap that allows emission of deep ultraviolet light. I messed that one up a few times. Single photon emitters, HBN can host a single photon emitters at specific defect sites, which are crucial for quantum communication and quantum optoelectronics. At the bottom right, you can see the world's first HBN-based deep ultraviolet LED. Thank you very much, and have a good day.